Hello everyone, welcome back to class number 2, power systems. Today we're going to talk about real and reactive power. So again, we're going to talk about single phase AC systems and real and reactive power. So if you have a single phase AC system right here, you have a load, this is your load over here, right? And we have a voltage across it with a VT, and current going to the load is IT. And we have the time domain expression here, both voltage and the current. Voltage has its own angle, theta V, and current has its own angle, theta I. So if you multiply them in time domain, we get instantaneous power. After some trigonometric manipulation, this will come to this equation right here. It's a long equation, but I'm gonna take piece by piece out of it. Again, one thing is that these are all RMS values, and you know the RMS values for sinusoidal signal is peak value divided by square root of 2, and for current and voltage both the same. So here's two parts over here. These parts over here, first part over here, we call it power going into the load. That means load is consuming this power. So this power is consumed by load. And this part over here, there is no net power consumption for this part. This is basically energy borrowed and returned by the circuit. So your load is borrowing power and returning it every cycle. So there is no net value for this part of it. All right, and also your theta over here, this theta over here is the difference between your voltage angle and current angle. So is theta basically theta V minus theta I. All right. So over here, now for the first part, this is the first part over here. If we do a little bit more manipulation, that comes to this equation over here. If you look at that, this part over here does not have any average value, it's 0. So average is 0 for that part over here, but this is your constant value. So if you take the average for this first part of the power equations, you have VI cosine theta. I'm just using V and I instead of two bar there. So that's the average part, and this is called your real power. So real power is basically VI cosine theta. Again, the theta is theta V minus theta I, is the angle difference between voltage and current. So this is the real power. This is the real power consumed by the load. Right? And the second part of it, if you look at the second part over here, there is no average value for this, for the second part, because it is sinusoidal signal, average is 0, so average is 0. But this over here, the magnitude part of it, we call it reactive power, that is VI sin theta. Reactive power only exists if you have a reactive element like a capacitor or inductor. So there's two things here. This is reactive power, remember that, and this is your real power, remember that too. So VI cosine theta is your real power, VI sin theta is your reactive power. All right, so now if you look into complex load, this right here, so let's see here, if you have load and you also have voltage, let's say load voltage, let's say is V 0 degree. That means I'm taking the voltage as a reference, which is 0 degree. So that is basically in your time domain. If you go with the time domain, you know from last lecture is Vm, which is multiplied by square root 2 cosine omega t. That's your load right there. So voltage right there. So now let's see here. If I try to find the current for this, if I try to find the current would be V over Z, right? My V is V 0 degree angle, and G is, let's say, is theta, for example, right? So if it's positive theta, if it's theta is positive, what happened? Look at what happened here. V over Z, that's the magnitude of the current, and your theta becomes negative. So that is, your current is, for this one here, your current is lagging. Your current is lagging. All right, so that means if your angle, if your Z theta is positive, your I angle, which is V over Z, is negative. That means current is lagging. So current is lagging. And if that happens, that means this is an inductive load. In inductive load, your current is lagging and your Q is positive. So that's is the inductive power consumed by the load. All right. Then if your theta is negative, let's say here Z is negative over here, then your I becomes V over Z positive angle, right? So that means your current is leading right now, and that is capacitive load, and Q is negative. The capacitor is supplying the reactive power, not consuming. All right. Now, so in the real power, you have P is VI. Real power is P, VI cosine theta. This cosine theta is called a power factor. If the factor is 1, that means your P equals normally is V times I. That's what you do for your DC circuit, right? So this is the factor that cosine theta value, as you know, can go from 0 to 1. So 1 is the highest, that's the highest factor. That's what we want. 0 is the lowest factor, which is the when cosine theta is 0, that means you don't have any real power. And reactive power unit is volt, ampere reactive. Real power is watt, and if you just multiply V times I, that means you're getting an apparent power. How they relate to each other? So if I draw a triangle here, so this is your P, this is your Q, and this is your VI. So that's a theta, right? So real power, reactive power, and apparent power, all three of them are related by a right angle triangle. See the right angle over here. All right, so let's talk about a little bit over here. Lagging and leading, okay? So let's say you have a complex load, Z, and is capacitive. So that you say R plus, you have a capacitor here. You know that capacitor here, J omega C, 1 over J omega C, right? Remember that XC is 1 over J omega C, and XL is J omega L, right? So it's basically R plus a capacitor, right? So if I now do the little bit magnification over here, I can say that is, let's do this negative over here. So R negative J over omega C. I can do that, right? We just multiply both numerator and denominator here with J. As you know that J squared is -1, right? So I can use that to find that. So now let's put some values there. Let's say value is, again, I'm going to put very easy value here. Let's say that, right? So with that, I can say that this would be your 14.14 negative 45 degree. That is capacity. This is capacitive load, right? Because I have a capacitor there. So capacitive load, right? And I can take another one. Let's make this one Z1 here. Let's say Z2 is inductive load, right? So I can there do it. XL is J omega L plus J omega L. So let's make it also the 10 plus J10. That will be 14.1445 degree, right? Right. So now, so I have a supply here and load here. This is load is your could be capacitive, could be inductive. So let's say that my load here, my supply is here is 120 0 volts, right? So now for capacitive one, I1 would be, for this particular example here, it would be 8.48 for the capacitive one. It would be positive 45 because 0 minus, let's do a little bit more math here so you can understand what I'm talking about. So it would be 120 0 over 14.14 negative 45, so it give you 8.48 positive 45. So that means your current is leading. It's capacitive, current is leading. If I go to the inductive one, I2, it would be same voltage supplying over 14.14 is positive 45 degree there, right? Should be 8.48 negative 45 degree amps, right? So this one is leading and this one is lagging, right? So that's how it works. Like in capacitive load, your current is leading. For inductive loads, your current is lagging. So now if I try to draw them to show you more into how it works. So let's say this is your voltage signal over here. So this is your VT, right? Then your current, capacitive current is leading. That means it's coming 45 degree before it. So it will be starting from here, and it's gonna peak here. So it will be like this, and it's gonna go let's see, it's gonna, sorry, it's not like that. So let's move it. Sorry about that. Let's try again. See your voltage here. See your current will start ahead of it. So I'm gonna take a different color here for the current. If you can see it, see, start ahead of it and peak ahead of it and go this like that and so on. So that's your leading current. So this is your I1T, leading current, right? For the lagging current, we're gonna start after the voltage. It should be starting over here. So I'm gonna take different color for that again. So it's gonna start from here and it's gonna go something like that. So that's your I2T, right? So now if you try doing the phasor domain, it's a lot easier to see in phasor domain. So let's say that this is your reference over here, right? And so reference is your voltage right here. So that is my voltage. Remember that is 0 degree angle, right? Then your leading current would be leading. So this way is positive, right? That are positive here. So your leading current would be somewhere here, which is 45 degrees. So somewhere here, right? So this would be I1, right? And your lagging current would be negative theta. That would be somewhere down here. That will be I2. This angle over here is 45 degree. So look at here, your capacitor current I1 is leading by 45 degree. Your inductor current I2 is lagging by 45 degree. All right. So here's the quick simulation over here. The quick simulation. We have two signal. Voltage is a reference signal. There's no angle difference there, and current has a negative 60 degrees, lagging by negative 60 degrees. So that's why this is the angle over here. So current coming after the voltage, and if you put them together, instantaneous value right here. So you can see that there's the average value is not, instantaneous value is not 0. So it has twice the frequency of current and voltage. And if you take only the real part over here, you can see that there's the average value for the real part, which is 2000 for this particular signal over here. And if you take the reactive part, there is no average value. The average is 0. All right. So that's the quick simulation for real power and reactive power. All right, we'll only talk about that. We already talked about that time dependent phasor domain. Then we're going to end here for this one, and we're going to go, we're going to solve this problem in the class, and we're going to go from there.